Alright, hello and welcome to this fluid mechanics problem. Today we're taking a look at this complex manometer, and we are told that one end is open to the air, and in this manometer we have air, water, and oil, and we are given dimensions shown in the figure for the manometer. So as we can see here, we have a manometer with an open end at the pressure of the atmosphere is 102 kilopascals. And then we're given dimensions. We're told water is in this section, air is in this section, oil is in this section, and then water is in this section here. And this section has a bend in the pipe at 30 degrees from the horizontal. So now using this information, we are asked to do three things. The first is to calculate the absolute pressure of the air at point A in kilopascals. Then we're asked to derive an expression for the pressure difference, PA minus PB, in terms of gravitational acceleration G, the column dimensions of H and L, the angle theta, and the fluid densities of the water and oil. And then we are asked to calculate the pressure difference using that previously derived expression. So let's get started. So the first part of this problem is to calculate the absolute pressure of the air at point A in kPa. And this concept of absolute pressure is a little different from gauge pressure. The difference is that you add the atmospheric pressure to the gauge pressure to get the absolute pressure. So we have this relation here, where the absolute pressure is equal to gauge pressure plus atmospheric pressure. So let's start with part A. So for part A, we want to find the pressure at A. So for this, we would start at the open end of the manometer here, and we are told that that is open to the air pressure of 102 kilopascals. And so to get to the pressure at A, we have to follow this tube down, across through the water, and back up into the point A. So remember, when we're doing manometer problems, we like to take our directions as down a pipe is positive and up a pipe is negative. And the reason for this is because as you move down a pipe, you have the mass of more material on top, more fluid on top, pushing down, exerting more pressure the further down you are. And it's negative going up because as the farther we go up, the less pressure there is from the fluid above, therefore the pressure decreases. Now we want to solve for the pressure at A. So for this, we start with the pressure at A. And starting at the open end, we know that there is air pressure, so we'd say the pressure at A is going to be equal to the air pressure. And we are coming down the manometer, so this air pressure is positive, and then now we reach this water. So we reach this water point, and we come around the bottom, go across the bottom and up, and this section here, the pressure is equal and opposite, because as we come down, we increase the pressure by this height of water. As we come across, the pressure is the same, and as we come up to that same point, we decrease the pressure by that same amount that we increased it. So it's equal and opposite, and therefore it cancels itself out and is just zero. So all we're really concerned about is the height of the water from the top of the left column here to the top of the right column here, and we're told that that is 44 centimeters. So now we have a fluid, and using the relation for pressure of a fluid, we know that the pressure of a fluid is going to be rho of the fluid times g, which is gravitational acceleration, times the height difference of the fluid. So in this case, this should be P air minus rho water g h, and in this case we're told that it is H2. So now we have this expression, and now we need to fill in the values for it. So we know that the pressure of the air is given as atmospheric pressure, and in this case we don't really need this expression of rho gh for the air, because with air, the height of the air in this class doesn't really affect the pressure that we have. So that's simply going to be PATM. And now we have minus, because we moved down the tube into the water. Now we have minus rho water, which is the density of water, which we are told is 998 kilograms per meter cubed. So we'd write that. Times G, so in this case we're in SI unit, so that's 9.81 meters per second squared. And notice how we have meters here and meters here, so that means we want to keep our dimensions in meters. So we'd have to convert our height to meters. So we have 44 centimeters, so to convert from centimeters to meters, we divide by 100. So 44 centimeters times 10 to the negative 2, that gives us meters. So now we can write this as PA equals PATM, and we're told that that is 102 kilopascals minus, we have 998 kilograms per meter cubed times 9.81 meters per second squared, and that just is 9,790 newtons per meter cubed times 0.44 meters is our height, and this means that PA is going to be 97.7 kPa. So that is the absolute pressure of our chamber of air in kilopascals. There we go. Now for part B, we're asked to derive an expression for the pressure difference from point A to point B. So we start this problem here. And in this problem, in this case, it's actually more helpful to start at point B and make our way back to point A. It doesn't really matter how you do this, but you can do this in any order. You can start at A, come down and go back up to B, or you can start at B, go up, come down, and then go up to A. It's really just personal preference, but I find it would be easier to start at point B here. So starting at point B, we have the pressure at B. And using our relation from earlier, where we know that the pressure of a fluid is rho times G times H, in this case we have water, so it'd be minus rho water, because we're moving up the pipe from point B, times G times H, and in this case our H is actually not just our length, so we'll come back to that. And then we come to the top of this section here, that's where we are, and now we come back down through the oil region, right? So as we come down, we are adding pressure, so it'd be plus rho oil, G and H2, because that is the height of the oil. Again, we can ignore the bottom part here, since they're equal and opposite, so we really only care about the height of the oil, which, sorry, is actually H1. And then we know that once we get through the oil region, so once we come through here and across to here, now we're at the air, and as mentioned earlier, the height of the air from here to here doesn't change the pressure in this case. So now we say that just equals PA. So now let's take a look at the H that we have for this section. It's not just going to be our L. So in this case, because we are told that this is at an angle of 38 degrees from the horizontal, we actually need to find the height or the y component of this triangle. And the way we do that is we'd use this section L as the hypotenuse and this angle theta of 38 degrees, and we'd set up a trigonometric relation using those two, and what we end up getting is that our height in this case, h, is going to be L sine theta. So now we can rewrite all this as PB minus rho water, so rho water times G, and we just said that h is going to be the height, which would be L sine theta, so L sine theta plus rho oil GH1, and now that equals PA. So now we have an expression for PB and PA. Now we need to set this up, and we want it in the form PA minus PB. So all we have to do is simply rearrange, so PA minus PB is equal to rho oil H1 minus rho water GL sine theta. So that is our answer for part B. That is the expression we are asked to derive. And now we can solve for part C, where we actually want the pressure difference PA minus PB. So now rewriting that expression, we get PA minus PB is rho oil times G times H1 minus rho water GL sine theta. And now we are told we have all our values, right? We have L, we have theta, we have H1, and we have all the densities we need. So we can rewrite this as 900 kilograms per meter cubed is the density of oil that we're given, times 9.81 meters per second squared is the gravitational acceleration, times H1, which we know is 88 centimeters. So 88 centimeters. And again, we want to keep all our units in terms of meters to make all the conversions and all the answers easier to use. So we'd have to multiply this by 10 to the negative 2 to get meters. And then we subtract the density of water, which we know is 998 kilograms per meter cubed, times G, 9.81 meters per second squared, times L, which is again given in centimeters, so we want to convert this to meters. So 52 centimeters times 10 to the negative 2 gives us meters. And then sine, and the theta we know here is 38 degrees. And the reason for that is because if we draw this triangle, that's not a triangle, sorry, like that, we have this is 38 degrees. We know this length is 52 centimeters, so we're concerned with this y height. And so using trigonometry, we say that sine of 38 degrees is equal to y over 52 centimeters. So therefore, we'd say y equals 52 centimeters sine 38 degrees, like that. So that's why we have this relation for h instead of just 52. So now solving for this, we get this first multiplication term simplifies into 7.769 newtons per meter squared. The second term becomes 3,134 newtons per meter squared, and that gives us 4,635 newtons per meter squared. Now you might be wondering, that doesn't really look like pressure. Newtons per meter squared doesn't really look like pressure, but if we think back to our dimensional analysis from a previous unit, we remember that the dimensions of pressure are equal to force divided by length squared. So then that means that we get force, which is newtons, length in meters squared, so this checks out. So this means our pressure difference here, PA minus PB, is equal to 4,635 pascals, or we can rewrite this in kPa as 4.635 kPa. And there's our answer.